Welcome again. Today we will discuss boron based reagents in organic synthesis. So, organoborane or organoboron compounds are chemical compounds of boron and carbon that are organic derivatives of BH3. Organoboron compounds are important reagents in organic chemistry, enabling many chemical transformations. The most important one called hydroboration. This is very useful reaction because the hydroborated products you can convert to other compounds. And CB bond has low polarity. The difference in electronegativity 2.55 for carbon and 2.04 for boron, and therefore alkyl boron compounds are in general stable though easily oxidized. Also, boron is not so electronegative. So, because of its lower electronegativity, boron often forms electron deficient compounds such as triorganoborans. Vinyl groups and aryl groups donate electrons and make boron less electrophilic, and the CB bond gains some double bond character. So, when vinyl and aryl groups are present, then boron becomes less electrophilic. Borane, diborane and organoboranes are classified in organic compounds as strong electrophiles because boron is unable to gain a full octet of electrons. This we know. There are 6 electrons on the boron because it is tri-coordinated. Unlike diborane, however, most organoboranes do not form dimers. Now, in this talk, we will first discuss synthesis of organoboranes, that we will discuss first from alkenes, then from Gigner reagent and borylation also, transition metal catalyzed borylation. Also, reaction based on organoborane we will discuss carbonylation, first we will discuss, then cyanidation. This is with carbon monoxide, this is with cyanide, and with other bidentate carbon nucleophiles. This also will discuss hydroboration, iodination, we will discuss borates, dichloromethyl methyl ether reaction, that we will discuss, Mattison boronic ester homologation, that is useful for allylic and cotyl boronic esters because they are stable, allyl boration. So, first we will discuss synthesis of organoboranes from alkenes. This is the hydroboration process. Hydroboration is a process in which boron reacts rapidly to alkenes, and this concept was first discovered by Dr. Herbert Charles Brown, and for his work he eventually received the Nobel Prize jointly with George Huttig for his discovery of the Huttig reaction in 1979. So, this is an pioneering discovery, that hydroboration, and they gave many other conversion to this hydroborated products, and that has been used in many natural product synthesis also. So, diborane as a pure compound is a dimer. BH3 forms 1:1 complex with ether solvents, for instance THF. In an ordinary electrophilic addition reaction of HX, Markovnikov's rule, which states that less electronegative atom, usually hydrogen, because X is the halide, so halide is the more electronegative and hydrogen is less electronegative. As to the least substituted carbon of the double bond, this determines regioselectivity. So, hydrogen adds to the least substituted carbon atom, that is the terminal carbon. So, when there is like this hydrogen hydrogen, then HX addition happens like this. So, X goes to there and hydrogen comes at the terminal. This is the Markovnikov rules. Now, with boranes, the hydrogen adds to the most substituted carbon because boron is less electronegative than hydrogen. So, in this case hydrogen is the more electronegative, when that is why it is called boron hydride. When a positive charge develops on the alkene on the most substituted carbon atom, that is where the partially negative charge hydrogen atom adds, leaving the least substituted carbon atom for the boron atom. And the so called anti-Markovnikov addition, because when the boron is replaced with a hydroxide group, the overall reaction is addition of water over the double bond in what appears to be an anti-Markovnikov addition. So, the positive charge is generated as the most substituted carbon atom. Now, here what happens? The hydrogen is the more electronegative here. So, the hydrogen adds to the most substituted carbon atom. That is what is happening here when this one unsymmetrical olefin is here, and now this is the terminal carbon. So, here BH2 will add and most substituted carbon hydrogen will add, and after H2O2 and hydroxide treatment, the BH2 can be converted to alcohol. So, this is actually formal anti-Markovnikov reaction, because ultimately hydrogen adds to the most substituted carbon and OH as the least substituted carbon. This method is generally used for the boron compound having very bulky substituents. One organoboron reagent that is often employed in synthesis is 9-BBN, that is 9-bora-bicyclo-331 nonane, which is generated from the reaction of cyclooctadiene and diborane. So, this is the reaction cyclooctadiene and this is the borane Me2S complex. They is acting as the boron reagent, and here two cyclopentadiene molecule reacts like this and you get a dimer of 9-BBN. So, hydroboration takes place stereospecifically in syn mode, that is on the same phase of alkene. So, this is very important, the syn addition happens in hydroboration reaction. Also, hydroboration of alkenes or alkynes is an efficient method for the generation of boranes, this we already told. However, the use of borane or borane equivalents leads to the conversion of only 33% of the starting olefin to product after oxidation or protonerysis. The remaining olefin is incorporated into boron containing byproducts. So, this problem can be solved if you use bulky like this one. The use of stoichiometric amount of 9-bora-bicyclo-331 nonane, that is the 9-BBN, as the hydroborating reagent provides a solution to this problem. So, this is an efficient hydroborating reagent, and that will give the products in high yield, and that means you can get high yields for the hydroborated products. Also, from Grignard reagent you can prepare organoboranes. Simple organoboranes such as triethyl borane or tris pentafluorophenyl boron can be prepared from trifluoroborane as the ether complex and the ethyl or pentafluorophenyl Grignard reagent. So, corresponding Grignard reagent you have to use like BCl3 trichloroborane or boron trichloride, and then 3 equivalent of ethyl magnesium bromide. Then what happens? 3 ethyl comes to the boron, you get the triethyl borane and 3 equivalent of MgBrCl. Similarly, boron trichloride can be reacted with pentafluorophenyl magnesium bromide and also 3 equivalent, then 3 pentafluorophenyl group comes to the boron and you get this is the boron reagent and 3 MgBrCl. Grignard reagent provides an essentially quantitative yield of the thiaxyl boronate ester. Like this one, there is a alpha bromo and this is the boronate, and now if you use just one equivalent, then you get a substitution reaction. So, this adds here and this is an useful thiaxyl boronate ester, and this is bulky thiaxyl boronate ester. So, we will see this thiaxyl boronate are useful in the migration because it will not migrate and it acts as an anchor group. We will see. By borylation, metal catalyzed CH borylation reactions are transition metal catalyzed organic reactions that produce an organoboron compound through functionalization of aliphatic and aromatic CH bond. So, this is also an important reaction, and metal catalyzed CH borylation reactions utilize transition metals to directly convert a CH bond into CB bond. So, this is very important reaction, transition metal catalyzed borylation, and aliphatic CH borylation, aliphatic CH bond also can be activated that means it can be borylated. And if you use this one, which is this B, so this is the bpene, and this is the long chain alkane, and here with this Cp star rhodium catalyst 150 degree centigrade, after 24 hours you get this terminal carbon atom is borylated, that is the terminal CH, here the CH, one CH is replaced by bpene, and this is the byproduct H-bpene. This was published in Science. Also aromatic CH borylation also is possible, like this one anisole. Anisole, if you treat with iridium quad methoxy dimeric and DT-BPY as a ligand in hexane room temperature, you get a mixture 2:1. So meta is more, here this hydrogen is borylated, that is the meta, and alternatively that is the para and meta. The para is getting borylated, then you get the para product, that is the minor. Boronic acid and boronic esters are common boryl groups incorporated into organic molecules through borylation reactions. And the most common type of starting materials that incorporate boronic esters into organic compounds for transition metal catalyzed borylation reactions have been general formula of ROT-BOR2, that is bis pinacollato-borane B2PIN2. So here also actually B2PIN2 is there, B2PIN2, and bis catecholato-diborane B2 catechol 2. So these are the structure, this structure I have already drawn, B2PIN2, and this is the B2 cat means cat is catechol, and pin means pinacol. So these are the short form B2PN2 and B2 catechol 2. They are the useful reagents that are used in the transition metal catalyzed CH borylation reactions. Now we discuss reactions of organoboranes. So various reactions on organoboranes are known because the migration is possible. The C-Br bond that can be migrated, that alkyl group can be migrated to other carbon atoms. So like carbonylation reactions of organoboranes with carbon monoxide, which is an ylide, gives rise to 3 possible rearrangements. Depending on reaction conditions, single, double and triple migrations of groups may occur, leading after appropriate workup to a variety of aldehydes and ketones as well as primary, secondary and tertiary alcohol. So these are very useful reaction, different kind of migrations is possible. In fact, 3 kind of migrations, single, double and triple, that is the single alkyl group, then 2 alkyl group and 3 alkyl group can migrate. So first we will discuss synthesis of aldehydes and primary alcohols via monomigration. So this is the reaction actually. So this is the trialkyl borane, and now when it reacts with carbon monoxide, it leads to formation of an 8 complex. So this is an 8 complex, and now boron get a negative charge and there is a positive charge of course with oxygen here, because carbon monoxide structure are like this, and now this is an electrophilic species. So and also this is a boron is negative charge. So this Br, this bond will cleave and this R will migrate to the carbonyl group, and now after migration you get the intermediate B. Now intermediate B, if you treat with some other reducing agent, hydride reducing agent such as lithium trimethoxy, aluminum hydride or potassium triisopropoxide borohydride, then this carbonyl group can be reduced and you get an intermediate like this C. This intermediate is useful for further reactions that we will see in the next slide actually. So reactions, this is the carbonylation monomigration we are discussing. Now oxidation of C, whatever we have seen. So oxidation of C by H2O2 gives the corresponding aldehyde product. So, if you treat with this compound with NOH H2O2, what happens? This one, so this will be O minus, this is the hydrogen R. And now, when you do this NOH H2O2, what happened? This there and oxygen will come. So, ultimately after hydrolysis you get this one. So, this is what? This is an hydrate, aldehyde hydrate actually. So, this will be in equilibrium with aldehyde. So, aldehyde hydrate is formed first, and that is actually aldehyde hydrate, and that is converted to aldehyde. On the other hand, if you treat with lithium aluminum hydride followed by oxidative workup, results in the presence of primary alcohol. So, if you treat again with hydride reagent, so two hydride, first with one hydride that gives this product intermediate actually, and now if you treat with lithium aluminum hydride, so another hydride will come here, and after NOH H2O2 treatment you get this one. So, what happens? So, after hydride treatment, this OM group will eliminate, and you get this one actually intermediate possibly, and now NaOH H2O2. So, this NaOH H2O2 you get here OH, because H2O2 NOH, what happens? The oxygen is formed here between CB bond. So, ultimately this goes to a primary alcohol. Alkenes used for the transfer reactions are hydroborated with 9-BBN. The resultant alkene 9-BBN derivatives undergo selective migration of the alkyl group when treated with CO in the presence of a reducing agent. So, now we will see an example, and 9-BBN is the boronating reagent actually. Applying this sequence to 2-methyl cyclopentane produces trans 2-methyl cyclopentane carboxylaldehyde with retention of configuration of the migrating group. So, this is 2-methyl cyclopentane its 9-BBN first is treated, and we know this is the less substituted carbon, here boron comes, and this is the syn addition. Now, after carbon monoxide and lithium aluminum trialkoxy hydride, so after CO means this is formed, and now what happens? Now, this group will migrate, because the 9-BBN that group does not migrate. The migrating power also we will discuss later, but primary migrates faster than secondary, secondary migrates faster than tertiary. Also there is a steric group in the 9-BBN. So, this group migrates selectively to here, and you get a carbonyl, then the reduction, and after that hydrolysis you get the aldehyde. So, this is followed here. So, after reduction, after carbon monoxide treatment you get this, then the rearrangement, and then the reduction makes this intermediate. After that NOH treatment you get this aldehyde, and this aldehyde you get the trans product. So, trans product is formed. Synthesis of ketones, double migration. If the carbonylation reaction is done in the presence of a small amount of water at 100 degree centigrade, a second alkyl group migrates from B to the adjacent carbon to furnish the corresponding ketone after oxidative workup. So, now we will see double migration. So, in the double migration, this is very important. If you do small amount of water at 100 degree centigrade, the reaction, same reaction, carbonylation reaction, you get this intermediate after. So, this is formed after first migration. Now, what happen if you put water heat, then this water will add to this boron center, and you get boron become negative, and when boron becomes negative, only possible that the alkyl group will migrate to the carbonyl, and this migration give this intermediate. After this intermediate, in this case you do not need any reduction, because already OH is formed here after double migration. two R groups migrated, and after that NOH H2O2 treatment. Similarly, here we will give this one ketone hydrate actually. So, OH and that will be converted to ketone. So, ketone hydrate will be formed first with NOH H2O2, this will be in equilibrium with the ketone. The use of thiaxyl borane 1,1,2 trimethyl propyl borane as the hydroborating agent permits synthesis of mixed trialkyl boranes and cyclic hydroboration of dienes. So, this is 2 alkenes, we will see 2 alkenes and this is diene. Like this is the thiaxyl borane. So, this is thiaxyl borane. This is, you can see there is a tertiary carbon group, that is the tertiary carbon alkyl group which is connected to BH2. Now, alkene 1, so after alkene 1, that is the R, means the R, after hydroboration you get this alkyl group R, and now there is a second R dash will come how? Now, if you put this R dash means that the olefin you have to treat, so that the alkene 2, then you get this trialkyl borane. Like here, you can get 2 different alkyl groups. So, that we will discuss in the next slide. Now, if you treat with a diene like 1,3-butadiene, what you get? You get this one, because this is 1 equivalent, and now boron adds to these 2 terminal carbon atom and you get this borane. So, example, hydroboration carbonylation sequencing followed by carbonylation generate a variety of unsymmetrically substituted ketones and cyclic ketones respectively. Since thiaxyl moiety exhibits low migratory aptitude in carbonylation, it serves as an anchor group. This we already discussed, that thiaxyl group will act as a anchor group, it will not migrate. Now, you see here are 2 different alkenes are reacted with thiaxyl borane. So, what happens with cyclopentene? You first treat, then you get this one, then you react with this one, a terminal acyclic olefin with acetate group is present, then you get this one. This is the 3 different group presented in the boron. This is the thiaxyl, so this will not migrate. Now, what will migrate? Now, these 2 groups can migrate. So, when you treat with carbon monoxide followed by H2O2 NaOC, so what will happen? You get this ketone. So, what happened? This is the mechanism same, that carbon monoxide makes this one. Now, first this group will migrate, and after that the second group will migrate. If you see the mechanism here, this is the double migration is happening here, and you get the ketone. So, double migration gives the ketone. Also, cyclohexanone, vinyl magnesium bromide, THF, water, you get this alcohol, vinyl alcohol means allylic alcohol, and now H plus H2O will give this diene. And now, thiaxyl boron, what will do? It will add to this. So, these 2 center, the hydroboration will happen. So, boron will add here and here. Now, you get this cyclic borane compound, and now if you treat with carbon monoxide. So, carbon monoxide with this, and after that 2 alkyl groups will migrate. So, first this group will migrate, this one and then this one. Also, if you see the geometry, so this is the hydrogen, this hydrogen is coming from borane, and this is the geometry. So, these 2 are seen, and after that you get this compound. So, this is the trans now, because this is coming from the S and this also coming from the boron. So, this trans geometry is formed, and you get the ketone after sodium acetate, this is base, and H2O2 you get the carbonate compound. So, the mechanism is same. What is happening here, the 2 different alkyl groups are used, acyclic diene. So, this is a diene Diene is used, the diene is used which is made the cyclic boron compound, and after carbon monoxide and base you get this ketone. Synthesis of tertiary alcohol via triple migration. Now, carbonylation of trialkyl boranes in the presence of ethylene glycol results in migration of a second and a third alkyl group to keep the corresponding tertiary alcohols after oxidation. So, earlier we have seen that in H2O you get double migration. Now, if you use ethylene glycol, so this is interesting because two OH are present that can satisfy the two coordination of boron, means, and another will be connected to alkyl group of course, and this can give triple migration. This will see that after carbon monoxide and this one ethylene glycol hit, what happens? See, these two OH is bind to boron and three alkyl groups are migrated. So, you get Cr3Br. So, three alkyl groups are migrated to the carbon atom. So, that is why Cr3 is formed, and after that NOH H2O2 treatment you get this tertiary alcohol. Hydroboration of polyenes followed by carbonylation and oxidations provide access to carbocyclic systems. Like here, a trine, three double bonds are present, and now what happened? The boron adds to here, and also to here. This carbon also is adding, so that you get this bond, right. So, boron is adding, so that I think this addition is taking place because of this favored conformation of two 6-member rings. And now, with carbon monoxide and ethylene glycol, so carbon monoxide, ethylene glycol, what will happen? This one will happen, this intermediate, and now this will migrate, and this will migrate. And now, what will happen? That boron will be coordinated to two OH groups of ethylene glycol. So, this intermediate will form, and after NOH H2O2 treatment you get this tertiary alcohol. So, these are very useful reactions, and you can get defined alcohols, primary, secondary and tertiary alcohols. Depending on the addition of simple water or ethylene glycol, you can change the course of the reaction. Now, we will discuss cyanidation, a useful alternative to carbonative route to ketones and trialkyl methanols from alkyl boranes. Nitrile anion, that is the CN minus, is isotonic with carbon monoxide and also reacts with R3B. However, the cyanoborate salts are thermally stable and therefore require an electrophile such as benzoyl chloride or trifluoroacetic anhydride to induce 1,2 migration. So, these salts, the cyanoborate salts are thermally stable and therefore require an electrophile such as benzoyl chloride or trifluoroacetic anhydride to induce 1,2 migration. So, this is important, you have to add trifluoroacetic anhydride, and we will see that depending on how much you add, that double or triple migration will happen. Formation of ketones and trialkyl methanols occur under milder condition than when using carbon monoxide. Hexyl group also here acts as anchor group in the preparation of ketones. And sodium cyanide must be dry. Excess of TFFA results in third migration, which results in the formation of trialkyl methanols after oxidation. So, in general it gives ketones or tertiary alcohols. Ketones in double migration and tertiary alcohol in triple migration, and the mechanism is a little bit different than carbonylation. So, what happens here also, first step is same, this 8 complex will form, and now because earlier we have seen the oxygen there is a plus, that is what this rearrangement was facile. Now, here this nitrogen has to be activated with trifluoroacidic anhydride. Now, there is a positive charge. Now, this can migrate. So, after migration you get this intermediate, and interestingly here also because of this intermediate, this nitrogen, again this is an electrophilic nitrogen. Electrophilic nitrogen. So, what happens? This bond is polarized. So, again another R group will add, and this oxygen will satisfy the boron tricoordination. See, this is the rearrangement is happening here. So, one R group migrating, and here the double bond is forming, and this oxygen is satisfying the trivalency of boron. That is the dual role of trifluoroacetic anhydride. Not only it activates the nitrogen, but also it satisfies this oxygen of trifluoroacetic anhydride satisfies the trivalency of boron, and after NOH H2O2 treatment you can get the ketone because two R groups migrated. Alternatively, if you use excess trifluoroacetic anhydride, another group will migrate, this group will migrate, and you get, so excess trifluoroacetic anhydride will give us this intermediate, because then the boron will have a negative charge. For this migration you have to first make the negative charge. So, what happens, this anion actually adds to the boron, this boron, and this makes this borate with a negative charge. Now, another migration will happen, also activates this one, COCF3 activates, because trifluoroacetic anhydride has two parts. So, COCF3 activates this one, and this adds to this boron, and after NOH treatment you get this alcohol. So, here triple migration and after double migration. So, that only if you use excess, then the triple migration will happen. So, this is limonene, and this is a chiral center actually. So, here two double bonds are there, where one is in the ring, another is the outside ring. And when it treated with hexyl boron in THF, what happens? This carbon and this carbon reacts with boron, this and this, and now you get this boron compound. See, this boron compound is formed, and here also I told chiral center is formed, is there. So, you get this kind of geometry. And now, what happened after CN treatment? You get this one, and after that CF3 will activate this one, COCF3, something like this, and now the migration will happen, and this group cannot migrate. We already told this is an anchor group, and after sodium hydroxide H2O2 treatment you get this ketone. Similarly, this one cyclohexene, if you just treat with boron THF, what will happen? Now, of course 3 cyclohexane will come, and you get this tricyclohexyl boron, which reacted with potassium cyanide to generate this intermediate. Now, if you use trifluoroacetic anhydride excess, so excess we have seen that excess the 3 migrations will happen, and after sodium hydroxide H2O2 treatment you get this one, alcohol. So, 3 migrations will happen when you have used excess one, because at the after double migration again this trifluoroacetate will add to the boron and will make feasible for the third migration, and after hydrolysis you get the tertiary alcohol. So, here double migration and here triple migration. So, we will discussing boron based reagents in organic synthesis, reactions of organoborans, and now we will discuss with other bidentate carbon nucleophiles. So far we have discussed carbon monoxide and cyanide. Now, reactions of organoborates and boranes involve the transfer of a nucleophilic group attached to boron to an electrophilic center either inter or intermolecularly. Alpha beta unsaturated borates as well as borates with a leaving group at the alpha position are highly susceptible to intramolecular 1-2 migration of a group from boron to the electrophilic alpha position. So, now if there is a bidentate ligand and if it is connected to the boron, now the one group from the borate will transfer to the alpha position, because that is the electrophilic position, and that is very important reactions, because oxidation or protonalysis of the resulting organoboranes may generate a variety of organic products including alcohols, carbonyl compounds, alkenes and halides. So, we will see some examples, and first we will discuss the different types. Boranes around are generally not nucleophilic enough to transfer an alkyl group to an electrophilic center. However, after nucleophilic attack, the resulting borate is highly nucleophilic. So, this is important, that after boron becomes tetracoordinated, so this is the nucleophile electrophile something. Now, this one will form. So, this when it is formed, then only the migration will possible. That only we have seen that boron when it is tetracoordinated, the migration is possible. If the nucleophile contains unsaturated functionality or a leaving group at the alpha position, one of the R groups attached to boron is able to migrate to the electrophilic alpha carbon. The propensity of an organic compound to migrate depends on its ability to stabilize a negative charge. So, alkynyl will migrate faster, because we know alkynyl is sp hybridized. So, that is the stable, and then aryl alkynyl, because they are sp2, and after that primary alkyl, secondary alkyl and tertiary alkyl. So, tertiary alkyl group we have seen in the thiactyl boron. So, that is why it does not migrate, it acts as a anchor group. Migration takes place with retention of configuration at the migrating carbon and inversion of configuration at the migration terminus, provided it is sp3 hybridized. So, this we have also seen, the retention of configuration will happen of the migrating carbon and inversion will happen at the migration terminus. So, this is the sp3, Y is an sp3 carbon, and now this is the borane, trialkyl borane, and after that you get this tetracoordinated borate, and there is a negative charge, and when negative charge is there, this group will migrate to Y and this will eliminate. So, this is eliminate or leaving group here when a carbon-carbon bond is present. And now, if there is a double bond here, so this is sp2 hybridized, and after that borane adds to this, you get this. And now, there is a double bond. So, when R migrates to this, the double bond becomes single bond, and so here Z does not leave. So, here because there is a single bond, Z is of course a leaving group, because it will has to leave, and here Z does not leave, Z stays in the molecule, and this double bond becomes a single bond. Now, sp hybridized, this carbon also can be used. This of course, we have seen that CnCO cases, and here what happened after migration, this become double bond. We have seen earlier imine or carbonyl compounds are forming, and here also Z does not leave, of course, Z does not leave, and so here double bond becomes single, here triple bond becomes a double bond. So, let us see some examples. So, first we will discuss this system where there is a sp3 carbon and one group has to leave. Alpha haloenolates are commonly used as nucleophiles. After nucleophilic attack at boron, the resulting ketoborane rearranges to a neutral enol borane. Upon protonalysis, a functionalized carbonyl compound results. The intermediate enol boranes may also be coenzed with electrophiles. So, this is an sp3 center. Alpha bromo ketones, that is the ketoenolate actually. So, this stays like this, O minus Br R dash. This reacts with trialkyl borane to generate the compound like this. Now, so I told that Z is a leaving group, so Br is Z here. So Br is Z, Z is leaving, and after leaving you get this one. So R group migrated to here, alpha carbon atom, and now what will happen? This will be equilibrium with this enol borane. So how it is forming? This oxygen is attacking to boron, and this carbon will become a single bond. So that is happening here. You get the enol borane. Here you get double bond, and this becomes single bond. And oxygen B bond is formed, enol borane. This enol borane can be treated with alcohol. So this is protonolysis. You get a ketone. So what happened? Actually, the bromo Br is replaced with a R group. So it is a higher derivative of ketone, and this is the byproduct. Alternatively, you can treat this also with electrophile. So then you can get electrophilic substitution also further. Reaction of organoboranes. Now more examples also will discuss this system. Treatment of trialkyl boranes with alpha haloenolate leads to functionalized ketones because the migration is stereospecific, retentive with respect to the migrating group and invertive at the alpha carbon. This method provides a means for the synthesis of enhanced pure alpha alkyl or aryl ketones. Like here, this is an borane. So here this one is formed after you treat 1-butene with 9-BBN. So after that you get this borane. Hydroboration happens to this center here and hydrogen here, then you get this borane. And now if you treat this one with the enolate of this bromoketone, then of course this center will add to boron and the N-butyl group will migrate, and after sodium acetate H2O2 treatment you get this one, the ketone. This was published in JACS 1969. So this mechanism is same, that the enol boron, so via enol boronate or enol borane. Via enol borane you are getting this compound. Alpha haloester enolates also add to boranes to eventually afford alpha functionalized products, however yields are slightly lower. Ester also can be used. Alpha dash dihaloenolates reacts with boranes to form alpha halocarbonyl compounds that can be further functionalized at the alpha position. So here the bromoesters has been used, and similarly the migration will happen. Similarly the first reaction followed by this N-butyl migration will happen, and after NOAC treatment, similarly here the ester is formed here, N-butyl ester, and this mechanism also via enol borane, by enol borane or enol borane ester. So here also you get this butyl group at the alpha position. So what is the formal reaction is happening here? So this one COOET, and now this one you get formally the butyl group is coming. So N-butyl group is a formal nucleophilic addition. So formal addition of butyl minus. However, here we have seen this is the 1-butene is used. So 1-butene is the butyl group that is adding to the 9-BBN, and now a borane is formed, and that is adding to this. First the tetracoordinated boronate is forming, after that butyl group is migrating. So this is the inherent chemistry, and that is the beauty of the borane chemistry, that you don't need a Gigner reagent for the substitution reaction. You can have a borane, where this group cannot migrate, it is an anchor group, and only the butyl group will migrate, and after that you get a substitution at the alpha position of the carbonyl compound. Here an sp2 system is used, and we have seen that when sp2 system is used, then this Z will not eliminate. And examples are ethyl diazoacetate reacts rapidly at low temperatures with aryl and alkyl dichloroboranes to give after protonolysis the corresponding ethyl aryl acetates and alkyl acetates in yields ranging from quantitative for the aryl to approximately 60% for the alkyl derivatives. So, this is the diazoesters. So, diazoesters actually can be written like this also. C double bond here. So, CC so these are neutral compound, and interesting here no base is required, no base is required. So, this is the best, there is a hydrogen CH minus CO2 ET and now this can add to the this one to the boron, and after rearrangement you get this one. So, we will discuss the detailed mechanism. What happens? First the Lewis acid coordination will happen, and there is a negative charge. There is a negative charge on the boron after the addition, and this nitrogen is a positive charge. So, what will happen? First this intermediate will form, and because the nitrogen elimination is leaving group is very facile, this migration will be very facile. So, this group will migrate to here and this nitrogen will eliminate, because nitrogen is a gas. So, this process is very fast, and after that what will happen? This coordination will happen. So, we have seen earlier with ketone, but also with ester this kind of A will happen, that this bond will break the carbon boron, and oxygen, this carbonyl oxygen will coordinate with the boron. That is what is happening here, and you get the enolate. After this, on protonolysis with alcohol, you can get this ester. So, this will be OH, and that is the enol of the ester. So, this will be the intermediate C OH, OET, CH and AR. Now, this will convert, this is the enol form of the ester. With carbon bidentate nucleophiles, now we will discuss when a triple bond is present, and here what will happen, like carbon monoxide systems or cyanide system, we have seen this triple bond, and the triple bond will first go to a double bond. So, here we will see the carbon that is the simple triple bond. We will discuss now C triple bond systems. Tertiary alcohols with two identical groups attached to the alcohol carbon can be synthesized through a double migration reaction of alkynyl borates in the presence of acid. Use of a single equivalent of acid and oxidation of proteolysis leads to ketones or olefins. So, depending on the amount of the acid, so here acid is required, and depending on the acid either mono or double migration. So, if you use more acid, then double migration, like see this system. So, this is already a boronate. So, this is obtained from B tri-N-butyl borane plus this one lithium this. So, this will give this boronate species, because negative charge is there. So, this is we are discussing now carbon carbon triple bond. Now, this is anion, this is adding. After that you have to add acid. So, after acid treatment what happens, this triple bond getting activated. So, acid is helping to activate the triple bond, and then the N-butyl group will migrate to the alpha carbon atom here, and this triple bond of course will be double bond, and this hydrogen is coming from the acid. This hydrogen will come from the acid, and now this intermediate will form. Again if you add more acid, so what will happen? Another group will migrate to the alpha carbon only. So, two N-butyl group at the same carbon atom, and this double bond will be single bond, and after H2O2 treatment you get the alcohol. So, this will be intermediate type N-butyl, and this is N-butyl, maybe Cl minus, and after that this on H2O2 treatment will add the alcohol. This was published in JOC 1975. Alkynyl boronates are useful intermediates that can be converted to either ketones or olefins after simultaneous migration and attack of the alkyne on a separate electrophile. So, another electrophile can be also be used. The electrophile and migrating group end up trans in the resulting alkynyl borane. Protonalysis of this intermediate generates olefins, while oxidation leads to ketone after tautomerization. So, suppose here similar system, this system is here. Now, here you do not treat with acid here you do external electrophile like alkyl bromide. So, what happens? Somehow this triple bond, because there is a bifunctionalization possible. So, this react under this condition, and after this addition, this is the migration is happening, this is the R1 and R3. So, R1 and this CH to R3 they are trans, they are adding in the trans fashion of the triple bond. So, they are adding trans fashion. After this addition you get this one, and now this compound if you treat with acid, just the protonalysis you get the hydrogen here. Alternatively, if you use H2O2 H minus, what will happen? Then R1 R2 you get the OH here, and this is actually ketone. R3, this is R2. So, you can get a ketone or a olefin depending on the treatment. If you do oxidative method, then you get the ketone, alternatively protonalysis you get the olefin. So, these are very useful method that a triple bond is getting difunctionalized with this boron system. Hydroboration, iodination we will discuss. Halides may be synthesized from organoboranes by activating with hydroxide or alkoxide, and treatment with X2. Two of the three alkyl groups attached to the borane may be converted to halide in the presence of excess base. But the use of dicyamyl borane, this is another sterically hindered borane, as the hydroboration permits the selective halogenation of only one of the hydroborated olefin. So, this is the dicyamyl borane. And when this 1, 2, 3, 4, 5, 6, 1 hexene is used for the hydroboration, and after that if you treat with iodine NOH methanol, you get this iodine, and iodine at the terminal carbon. So, this is a very useful reaction, because if you want to do HI addition, then the iodine will add. So, HI, the iodine will add actually here. So, for terminal carbon atom, the iodine is attached. For that, of course, you have to use the boronation. And this is the mechanism that after hydroboration, you get this one. This is the terminal carbon boron is attached, and now what will happen? The NOH make the, this is actually N pentyl, this is the RR, this intermediate OH, and after iodine what will happen? These are the bulky groups, this will not migrate, also this is secondary alkyl group, this is primary. So, this group will migrate to the iodine and you get this one. So, here the migration happens to the iodine, and I minus is treated is reacting with also sodium plus, you get the sodium iodide byproduct, and this one OH hydroxy containing diamyl boron is the byproduct, that is what the OH is adding. So, OH is helping to generate this boron minus charge here, tetracoordinated borate, and that is reacting with iodine. After that migration is happening. Reaction of organoboranes with nucleophiles containing more than one living group results in multiple migration. Thus, on treatment of R3B with alpha alpha dichloromethyl methyl ether in the presence of a sterically hindered base such as LiOCet3, all three groups are transferred and oxidation of the product affording the corresponding tertiary alcohol. So, this is also not only triple bond, here what happens, this Cl OMe and negative charge. So, all three groups are living group, this is also living, this also living, this also living, and ultimately living you get this one after NOH H2O2 treatment, because this B, maybe this RR and this is the R group, 3 R group is added. This might be Cl, this might be Cl, and now after hydrolysis you get this one. LiCCl2OMe is generated in situ from dichloromethyl methyl ether with lithium triethyl methoxide. Homologation of chiral alkyl boronic esters with dichloromethyl lithium introduces a chiral center while forming a CC bond. The required boronic esters are readily accessible from Gigner reagents and trimethyl borate or from lithium reagents and triisopropyl borate. Hydrolysis of the resultant alkyl boronic ester gives boronic acid, and further reaction with R or S phenyl diols furnishes the stable RS phenyldiol alkyl boronic esters. So, this is the trialkyl borate with Gignard, it generate this one tetracoordinated, after H plus you get this boronic acid, and when it treats with chiral alcohol you get this alpha phenyldiol alkyl boronic ester. And Mattison boronic acid homologation, the chiral directing groups are phenyl diols derived from osmium tetroxide catalyze oxidation of alpha pinene and alpha pinene with trimethyl amine oxide or with NMO. The S and R notation shown in the abbreviations refer to the configuration of the chiral center in the alpha chloroboronic ester using the appropriate phenyl diol. So, alpha pinene plus alpha pinene when it treated with osmium tetroxide it generates this diol, and this is the chiral diol. Similarly, minus alpha pinene with osmium tetroxide catalyst, and this is the N oxide, you get this cis diol and chiral, and also this osmolation is happening from the opposite face of this group. And these are useful reagent, this chiral one, because you can control the chiral. So, this is chiral boron ester or chiral boronic ester. And now, if you treat with LiCH-Cl2, tetracoordinated boron borate complex will form here. Now, because you have a chlorine, 2 chlorines are there. So, what will happen? The rearrangement will happen with zinc chloride also. If you put zinc chloride, then this group will migrate and this will form 1 chloroalkyl boronic ester. And again after treatment with Gignard or R-Li, another group can be brought, and that gives the boron negative charge again borate complex, and second alkyl group. So, this is the first migration, and here second migration, and here also you see the inversion is happening. So, here inversion is happening because now this is a chiral center, and now the inversion is happening because initially it was not a chiral center. This is a chiral center, and you get the inversion, and this is the secondary alkyl boronic A star, and all these processes are selective, and after that you get this alcohol in greater than 97% E. So, the salient feature of the boron ester homologation, the boronic ester E, this can be also used as a starting boronic ester. So, the cycle can be repeated to introduce a second chiral center. This can be also used for this again treatment with LiCH-Cl2, you can get some products here from here also. And zinc chloride catalysis is important, the rearrangement in giving improved diester selection. And this homologation retrosynthesis analysis of homoallylic alcohol, this can be generated from the aldehyde and allyl organometallic reagent and this allyl boronic ester. So, allyl organometallic reagent mostly use allyl boronic ester, that can react with aldehyde. Borates, now we discuss borates, trialkyl boranes can be oxidized to the corresponding borates. One method for the determination of the amount of CB bonds in a compound by oxidation of R3B with trimethyl amine oxide or 2BOR3. The trimethyl amine form that can be titrated. So, this way you can Me3N which is liberating, that can be titrated. Boronic acid react with potassium difluoride KH2 to form trifluoroborate salts, which are precursor to nucleophilic alkyl and aryl boron difluoride CrBF2. The salts are more stable than the boronic acids themselves and used for instance of alkylation of certain aldehydes. Like this one, when it used with trimethoxy borate, then you get this allyl boronate species. After HCl treatment, you get the allyl boronic acid, and after treatment with KHF2, 3 fluorine comes to the boron, and this product is stable. This was published in JOC, and this is very useful allylating reagent. So, paranitro-benzoaldehyde when treated with allyl BF3 potassium reagent, and this is a Lewis acid, then you get the allylation in 96% yield. This was published in Pure Applied Chemistry. So, today we have discussed first the boron synthesis, and that is the first thing is the hydroboration, that is the boron addition to double bonds. Followed by we have discussed the Grignard addition. By Grignard addition also you can, because Grignard reagents can add to the boron, and now you can generate the boron compound. Also via transition metal catalyzed CH borylation, because this is very important that CH bond, not only aromatic, the alkane CH bond can also be borylated, and we have seen that B2PN2 they are mostly used, and with iridium catalyst or rhodium catalyst you can get this borylation, and mainly for long chain alkanes the terminal carbon atom getting borylated, and for aromatic system you can get meta para mixture. Then we have discussed different reactions with boranes. So, first we have discussed carbonylation. So, carbonylation, because carbon monoxide it is actually bidentate synthone. So, it can react and make the boron negative, and after that alkyl group can migrate. So, after alkyl group migration you can reduce with a reducing agent like triethoxy lithium aluminum hydride, and then after hydrolysis you can get either aldehyde, and alternatively with further treatment with another reducing agent like lithium aluminum hydride and then NaOH H2O2 oxidative condition you can get primary alcohol. Now, this is the mono migration. Also double migration is possible when you treat with water, then that double migration is possible and you can get a ketone. Also triple migration is possible and trialkyl 3 alkyl groups can migrate, and this case you can get like tricycloalkyl alcohol or tertiary alcohol, and in this case you have to use the ethylene glycol. So, ethylene glycol is acting as the satisfying the bidentate, because ethylene glycol is bidentate. So, it satisfies two coordination of boron and another is connected with another bulky alkyl groups. So, this is important, and now then we have discussed the cyanide. So, here the also depending on the trifluoroacetic anhydride. So, if you use one equivalent of trifluoroacetic anhydride, then the double migration is happening, because already one coordination is satisfied from the trifluoroacetyl group. So, double migration is always possible, and triple migration also is possible if you use excess trifluoroacetic anhydride. And then we have seen the other sp3, sp2 and sp systems, other bidentate nucleophiles, and like alpha bromo ketone enolate or alpha bromo ester enolate has been added to boron, and we have seen the substitution of the boron by the alkyl groups. Like N-butyl group can be migrated when the bulky other like thiaxyl boron is used as the anchor group, then selectively only the N-butyl group can migrate. Also, we have seen that sp2 system like the diazo ester, that can also give the reaction, and here also we have seen the migration of a alkyl group, and then you can get the substitution at the ester group. Also, we have seen the triple bond like CC triple bond can also give the reaction, and then if you put the acid, then the monomigration will happen. If you use excess acid, then double migration will happen and tertiary alcohol will form. Also, you can put external electrophiles, so that electrophile can be added to the triple bond, and the finally a olefin with trans geometry is formed. And then we have seen that dichloromethyl methyl ether, that is also useful, and you can see the migration here possible. 3 groups can migrate, and tricyclohexanol, tricyclohexyl methanol is formed also by this method. And then we have seen the Matteson's Matteson boronate compound, and these are good compound with chiral boron compounds, because there is a alpha pinene that derived alcohols, diols are there, and that can give the products when treated with LiCCl2. Then this double migration will happen, and you can get that secondary alcohol in very good yield. Thank you.